Okay guys, so this will be sample problem number 3 for shear and bearing stresses. We have here this simple problem. We have here a wheel and a somewhat a belt-like structure that is surrounding this wheel. And we have a shaft from this point, let's say this is point A all the way to this point that is point B. And if we will try to look at it much nearer, we have a somewhat like a shaft, which is this inner circle corresponds to this shaft here on the right side of our free body diagram. And we have here also a pin that prevents the wheel from rotating counterclockwise, countering it is torque equivalent to 2200 Newton meter. So we have this inner shaft and a locking pin, or let's say that is a key that prevents the wheel from rotating. And the problem wants us to simply look for the value of this B. Okay. We have this somewhat rectangular shaped key that acts as a lock for this rotating mechanism. And we have the diameter of the shaft, which is this one inside this outer ring. We have here equivalent to 60 millimeters diameter shaft. We have the height of this key equivalent to 10 millimeters. We have the length of the key equivalent to 70 millimeters. And of course, the width of this key is equivalent to B. So the problem wants us to simply solve for the value of B for this problem that we have. Don't forget, we have 200 millimeters diameter for this wheel. I applied torque equivalent to 2200 Newton meter. Okay, so let's try to solve this one. So in order for us to solve this problem, we need to consider first what are the possible parameters that involved in this problem. So we have the measurements of the inner shaft and the keys itself. We have a given torque, and what else? We have the free body diagram of the problem itself. So let's try to consolidate this portion of the free body diagram, because what we need is to simply solve for B, and the problem gave us an allowable shear stress equivalent to 60 megapascals. So it means to say we have a given for tau is equals to 60 megapascal. So that's the allowable shear stress for the key. Okay, 60 megapascals corresponds to the allowable stress that can be imposed on this key. Okay, this locking a component of this whole mechanical rotating machine. So let's try to draw the two-dimensional view of this free body diagram. Okay. So if this is the key, going like this, okay, circular. We have here the center point. Just to somewhat emphasize the key, I'm just going to draw it like this. Okay, this is the key. Okay, and the diameter is 60 millimeters, so we can simply assume that the radius is equivalent to 30 millimeters. Okay, so that's why 60 divided 2 is simply 30 millimeters. We have the height of the key, which is equivalent to 10. Okay, this one is 10 millimeters, and this one is obviously B. Okay, so let's try to emphasize everything. We have an applied torque equivalent to 2200 Newton meter. Okay, it goes like that. Torque is equals to 2200 Newton meter. And what else? I guess that's it. And the problem wants us to simply solve for required. Okay, the required is B. So how are we going to solve this one? Now, based on the givens that we have, the problem gave us an allowable shear stress for this key equivalent to 60 megapascals. And obviously, if we're going to solve this width of the locking component that we have in our free body diagram, we need to consider first the forces that is acting on this locking key. Means to say, if we have a given allowable shear stress, let's try to draw this on a three-dimensional uh, perspective. This locking key should be like this. Okay, it should be like somewhat like this. I'm just going to draw this much better, like that. So this one is 70 millimeters, and this one is B obviously, and this one is 10 millimeters. So if we are given a allowable shear stress equivalent to 60 megapascals, it means to say that we are somewhat concerned with shear forces, right? Because this is the only parameter that was given to us in terms of forces. And don't forget, we have this torque 2200 Newton meter. So if we are given this torque equivalent to 2200 Newton meter, if we try to remember the formula for the torque is just basically force multiplied by the perpendicular distance. Means to say that if we set a certain radius of this circle, let's say for example going this way, having a radius equivalent to 30 millimeters, it means it has a force that is acting perpendicular to that distance from our reference point, right? So that should be F. So this F is basically this one, and D is basically the radius. Okay? So that if we try to multiply these two, we will have a result equivalent to 2200 Newton meter, right? And this F, if it somewhat interacts with our key here, so let's try to look at that on a three-dimensional view. Okay. Means to say that this is our neutral axis. Okay, it passes through the center of our object, and this F rotates somewhat like this, like that. So that's the torque T. If we try to multiply F and D, we can somewhat look for the tangential component for that one. That should be F. And this F interacts with the surface area of this key, right? Because this area of the locking key is somewhat subjected to shear forces by this F. Okay? Because it's somewhat going to pass over this portion of the surface area on top of this locking key. So this one, we can simply say that this is the shear load applied on our locking component. So let's try to solve for F, because that is the shear force interacting with this surface area of our locking component. So let's try to solve for F. So F is basically torque divided by distance. So torque is 2200 Newton meter divided by the distance, which is 30 millimeters. If we are going to convert that into meters, that is simply 0.03 meters. So simplifying, this one should be approximately 73,333.33 newtons. Okay. So means to say that there is a force acting parallel on this cross-sectional area, okay, of our locking component equivalent to 73,333.33 newtons. So I hope that's clear on why did it became like this one, because it seems easy, but there are some trickiness. If we consider the fact the free body diagram is look like that, then solving for B, and what is the purpose of this torque and this allowable shear stress equivalent to 60 megapascals. So again, what we did here is to simply solve for the shear force applied on our locking component, which is acting parallel on this cross-sectional area equivalent to 73,333.33 newtons. But that is not what we need. What we somewhat required is this width of the locking key. So this 73.33 kilonewton is important for us to solve for that B. So I'm just going to erase this one so that we can have some space to solve. Okay. So now, after solving for F, we can now apply the formula for the shear stress, which is tau is equals to F, or the shear load applied on our locking component, divided by the area of influence, which is this portion. So all we need to do is to look for the geometrical parameters concerning the shape of this upper portion of our locking component. So obviously that would be at the area portion, right? Area is equals to the force divided by the shear stress. Okay, and then proceed. Let's try to dissect this A, which is simply this length of the locking component multiplied by B, right? So that should be 70. Let's just try to convert it directly. Okay. So this one is the length, okay, that is the length multiplied by the width, which is B, is equivalent to force over the allowable shear stress. Then solving for B, B is equals to F divided by the shear stress multiplied by the length of this locking component. So let's try to substitute that. F was 73,000. Okay, 73,333 newtons, 33.33 newtons divided by 60 megapascals. Okay, 60 megapascals multiplied by 70 millimeters, that is 0.07 meters. If I'm not wrong, yes, that's 0.07 meters. And B, okay, B is equivalent to 0.01746 0.01746 meters, or you can simply say that in terms of millimeters, B is equals to 17.46 millimeters. So the answer for this problem is 0.0746 meters, or 17.46 millimeters. So I hope that is clear for this sample problem.